Hey everyone, Mrs. Hanson once again, and we're picking up our lessons on ions. And as I said as I concluded the last video, we're going to learn how to use the periodic table to help us predict charges based on their location. So here's some key items as we make our next steps. Elements in the same group, which are meaning that they have the same column. So same group is the same column on the periodic table. That means they're in the same family, if you will. That means that they're going to have the same number of valence electrons. All atoms in the same column, which is the same as saying same group, same family. They all have the same number of valence electrons. That's why they live where they live. And that helps us predict charges as ions develop based on the location of their charge. For metals in group 1A, we know that they have one valence electron. Group 2A means they have two valence electrons, and in group 3A, they have three valence electrons. The metals will always form positively charged cations. We've seen that trend from our last set of drawings. Metals form positive ions by losing electrons. And the nonmetals gain electrons. They form anions. So we're learning that nonmetals will always gain electrons. And when they gain electrons, that means they form negatively charged anions. And they do so with this little formula of 8 minus the group number. So for instance, oxygen, for example. Oxygen lives in group 6A. He's in the 6th column. So you can see that oxygen would have 6 valence electrons. How many electrons would it like to gain to get to that magic number 8? Well, I can see a spot for 2 more electrons, and when it does so, 2 extra electrons makes it end up with a -2 charge, 2 extra negative charge, not yet balanced by protons. 8 minus the group number tells me the negative charge that it's going to be. So the anion charge is always negative. To find out the magnitude of the charge, 8 minus 6 gives me 2. So the magnitude of the charge comes from this particular formula, knowing that the magnitude is always negative for extra electrons. So the charge is -2. I can find out how negative it is by seeing how many electrons it would like to take in to get to 8. So for instance, these elements, just as a kind of a pattern, we see if it is in the first column, group 1A, meaning that any element, such as lithium, 1 valence electron, sodium, 1 valence electron, potassium, rubidium, cesium, they all have 1 valence electron because they live in the very first column. Here's lithium, sodium, potassium, rubidium, cesium, francium, all in that first column called 1A, meaning 1 valence electrons. They will lose 1 electron to form a +1 charge. Group 2A, these are the beryllium, magnesium, calcium, strontium, barium, radium. Group 2A has 2 valence electrons. When they lose 2 electrons, they form a +2 charge, Be +2, Mg +2. Go to the metal of aluminum, gallium, indium. Notice that boron is not a metal. He's actually a metalloid. And so therefore, he will not be positive. He'll actually be negatively charged, boron. But in the box of aluminum, this is the group 3A, they will lose 3 electrons. Aluminum will be a +3 charge. So there's our pattern of saying aluminum +3, gallium +3, indium, and so forth. Any element in group 1A forms a +1 charge. Any element in group 2A, a +2 charge. So on our periodic table, we can see a pattern of the group A elements. The group A elements, I tried to write A and it came out messy. These are what we refer to as the representative elements. They represent their valence electrons. And that helps us predict the charge that they carry. So the representative elements represent their valence electrons, meaning lithium, sodium, potassium, rubidium, all of those in group 1A have one dot. That's one valence electrons as atoms. When they lose that valence electron, they form positive ions. We call that lithium ion, sodium ion, potassium ion, rubidium ion. All have lost one electron and form a +1 charge on their ion. That's the group 1A. Group 2A, notice here we could think about this as just being a +1 charge for the entire column. In group 2A, you have beryllium, 2 valence electrons, magnesium, 2 valence electrons, calcium, 2 valence electrons, strontium, barium, all of these live in group 2A and thus have 2 valence electrons as neutral atoms. Atoms are unstable. They want to lose electrons to form a noble gas configuration. They're going to lose 2 electrons to become like a noble gas, and the resulting charge for the loss of 2 electrons is a +2. The beryllium ion, no dots left, but a +2 charge. Magnesium, no dots, it lost them, but it results in a +2 charge. Calcium, +2. Strontium ion, +2. And the barium ion, +2. So all of these in the column below are all +2 charges. I mentioned that the staircase separates the world from metals and nonmetals. Boron is a non-metal. It's a metalloid, a semi-metal, so it will not be forming a plus charge. But aluminum, who lives in group 3A, would lose 3 electrons. So group 3A, the metal, remember we have to start with the metal, has 3 valence electrons. Gallium, 3 valence electrons. And so they actually lose all 3 of their electrons to form ions. Aluminum ion, +3, no dots. It lost those 3 electrons. And the same trend continues for gallium and so forth. So with confidence we know aluminum is +3. We know beryllium's entire column is +2. And we know hydrogen's entire column is a +1 charge based on the location for the group A representative elements, those metals forming positive charge. Now let's talk about the nonmetals. And we understand nonmetals gain. Metals lose, making positive. Nonmetals gain, making negative ions. We said that any element in group 6A, this would be oxygen, sulfur, selenium, they have 6 valence electrons. How many would they like to take in to get to 8? You can see 2 empty spots. So when oxide forms with its extra 2 electrons, had 6, needs 2 more to get to 8. What do I add to get to the 8 that it would want? Well, I add 2 more. Remembering that adding extra negative charges results in a net negative. Sulfide ends with 8 dots and carries a -2. 6 of those were its original, and it gained 2 more from a metal who's transferring them somewhere. And of course then the halogens, group 7A. Any halogen such as fluorine, chlorine, bromine, or iodine starts with 7 electrons. It has room to take 1 more in. You'll notice that it has a -1 net charge. So thinking about fluoride, chloride, bromide, iodide, all -1s. Group 7A are known as the halogens. They have 7 valence electrons, meaning they want one more to get to 8. When fluoride gains that electron, it now becomes like neon. When phosphide, sulfide, chloride gain electrons, it now becomes like argon. So we're getting that noble gas configuration as we work towards the periodic table's S2P6 configuration. Oxide, sulfide, selenide, all -2s. Nitride, phosphide, see how they have 5 valence electrons? They're going to gain 3 more to get 8 in the configuration. Lithium's families, all +1. Beryllium's family, all +2s. Aluminum, +3. When we hop the border, we go from the world of positives to the world of negatives. How many electrons does it take to get to 8? 1 more for group 7, 2 more for group 6, and 3 more for group 5A. Use the group number to determine the charge on an ion derived from each of the elements. The first is magnesium. All we need to do is locate where magnesium is on the periodic table. Magnesium lives in group 2A. It will lose 2 electrons to become a +2 charge. When magnesium, who is number 12, loses 2 electrons, it then has 10 electrons. It will become like neon. Loss of 1 brings me to sodium. Loss of 2 brings me to neon as the noble gas it will resemble. Iodine. Well, all I need to do is find iodine on my periodic table and I'm able to predict its charge. With a periodic table that has all of the elements in it. See it, neon, argon, krypton, xenon, neon, argon, krypton, xenon, neon, argon, krypton, xenon, and radon. So when we fill those in, we were looking for the element iodine. When iodine forms a negative charge, it gains 1 electron. It has 7, wants to have 8. It becomes like the noble gas xenon. So iodine is written as I-1. It has the same negative number of electrons as the noble gas xenon. Iodine is number 53. Xenon is number 54. Let me go back here. 53 to 54, showing the iodine gaining an electron to become isoelectronic. And that's just a fancy vocabulary word to say same number of electrons. Iodide has the same number of electrons as the noble gas xenon. Iodine has 53 electrons. Iodide has 54. Who's next? Selenium. That elemental symbol is Se. It gains 2 electrons. It has 6. It gains 2 more to become like the noble gas, krypton. Selenium becomes selenide. And selenide has the same configuration as the noble gas, krypton. So selenium gaining 2 electrons becomes isoelectronic as the noble gas, krypton. And rubidium, the elemental symbol for rubidium is Rb. Rb is in group 1A on the periodic table, meaning it had 1 valence electron. Loss of 1 made it a +1. So minus an electron says go back. And who is the previous noble gas that you passed through? And that would have been krypton. So rubidium was a +1. It lost an electron. So back up 1 row to find the previous noble gas. And you found it to be isoelectronic with krypton. Something interesting, selenide, Se -2, and krypton, and rubidium with a +1 are all isoelectronic. They all have the same number of electrons. How many is that? Well, krypton has 54, up here, krypton has 36 electrons. Selenium had 34, but gained 2 to become 36. Rubidium had 37, but lost 1 to become 36. And krypton already had 36. Those are all isoelectronic elements and ions. Now, we've purposefully left out those shorties in the middle, those transition elements, and it's time to bring those into the conversation. The trick with the group B elements, which are called transition elements or transition metals, because they transition their charge. They do not have a fixed charge. They have a variable charge. In other words, the positive charge on metals, and remember the transitions, shorties in the middles, these are still metals, and metals are always positive. So even though they're in the short columns in the middle, we can still see they'll always be positive, but we don't know, based on where they live, what positive charge they have. It really depends on what they're bonding to. So, metals of variable charge, those are the transition metals, transitioning their electrons between energy levels. Remember, these are D sublevels, so they have an opportunity to lose more than one type of electron depending upon what it's bonding to and how many the negative ion would like to receive. So this variable charge, how do we tell a reader what positive charge is on? How many electrons were lost during this exchange of electrons? And that answer lies with the Roman numeral as part of the name of the ion. So transition elements require a Roman numeral in the name. Now I say that, and there's 3 exceptions. Let's get this written first and then talk about what I'm saying. For instance, the element chromium, the elemental symbol for chromium is Cr. If I were to look at the element chromium on the periodic table, I would not know its charge by where it lives. Because it's a short element in the middle, it's a transition element, I am unable to recognize its charge based on a periodic trend. The only ones I know with certainty, column 1, those are +1s. Column 2, those are +2s. I know aluminum, that's a +3. I know fluorides, all -1. The oxide family are all -2. The nitrides are all -3s. Those I know based on the location. Group A's represent their valence electrons, but transition elements do not. So just by looking where chromium lives, I don't know its charge. I don't know iron's charge. I don't know cobalt's charge. It lives in the heartland of, I don't know your charge by where you live, because you have a variable charge. I can't tell by location. The purpose of a Roman numeral as part of the name of the ion is to let the reader know the charge on the ion. If I'm writing a formula and I want that chromium to represent the loss of 2 electrons, I have to tell you by naming it chromium, Roman numeral 2, ion. If I had just said chromium ion, you would have no idea the charge that it carried. But in nature, there's a second way, a second kind of charge that chromium could carry, and that's a +3. So if I'm looking at a formula and want the reader to know that it's carrying a +3 charge, I'm going to let you know by naming it chromium 3 ion. In nature, iron can be a +2 or iron can be a +3. It just depends upon its, what it's bonding to. So to let you know what ion I'm referring to, I name it. And I do so by using a Roman numeral to represent the charge that it's carrying. So Roman numeral 3, oh, you mean the iron +3 ion. Chromium 2, oh, you mean the chromium +2 ion. Nickel 2, nickel 3. Manganese 2 or 3. Cobalt can be a 2 or 3. Gold can be a 1 or 3, and so forth. So we have a variable charge in the heartland here of the shorties. You do not know the charge by locating the elements in the short columns called the transition metals, even including tin and lead over there in group 4A. They have a variable charge. In nature, we have a tin 2 ion. And we have a tin 4 ion, and the same for lead. Lead, Roman numeral 2, lead, Roman numeral 4. You don't know until I tell you by using a Roman numeral. The next thing I want to challenge you to do is the following, and that's to find these 3 exceptions to the Roman numeral. There are 3 exceptions when I say that all transition elements require a Roman numeral. There's 3 that break that rule. The first is the element zinc. Zinc will always, 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 always be a +2 ion. Always. There is no variable charge. Therefore, do not give it a Roman numeral. It doesn't need it. It's always +2. The next is cadmium. Cadmium +2 does not receive a Roman numeral. It doesn't need it because it's always +2. And the third is silver, Ag+. Do not give a Roman numeral to silver because it's always +1. We know that. You do not tell me that. I already know it, so no Roman numeral. Silver, zinc, and cadmium are the 3 exceptions to every transition metal, all the way over to the border, including tin and lead, require a Roman numeral in their name. Not zinc, silver, cadmium. So remember, these are all positively charged. They're metals, and metals are always positive. Alrighty. So as we think about naming, I wanted to share what your text represents also as a kind of a common name and the IUPAC name. Now this will be the recommendation. IUPAC, the International Union of Pure and Applied Chemistry. Think of this as the systematic approach of naming compounds, where these are common names based on the elemental, usually Latin name. But all I wanted to share with you is, if, for example, the element chromium, who we said lives in the heartland of, I don't know your charge by where you live. I don't know your charge. So I'm going to tell you in its name. If I want you to know I'm referring to chromium +2, I'm going to use a Roman numeral in its name, the chromium 2 ion. If I want to let you know that it's carrying a +3 charge, I will tell you that with a Roman numeral in its name. To name chromium 3+, you would say chromium 3 ion. A Roman numeral is required as part of its name. Remember, the formulas do not get Roman numerals. The names get Roman numerals. Copper can be a 1 or a 2. Copper 1, copper 2. Iron is a 2 or 3, so we say iron 2 or iron 3, and so forth. Now, in terms of common names, we have a different type of ending, no Roman numerals, but a more of a Latin feel to it. Chromus, chromic. Notice that the lower charge, which is the +2 ion for chromium, as compared to the +3 charge, the lower the charge gets an us, the higher charge gets an ic. Chromic or chromous. Here's a copper +1, cuprous, the lower charge, +1. Here is +2, so we name it with ic. That's called cupric, +2. Ferrous, ferric. Mercurous, mercuric. Stannous, stannic. So I just wanted to share that there is kind of an order to these comic names. The OUS ending is a lower charge than the ic ending, but we will be using the IUPAC system for naming using the Roman numerals as part of the transition metal names. So I'm going to just do a series of practices to get us thinking about these shorties in the middle, these elements that transition or have a variable charge. And these are metals, so they'll always be positive. So I'm going to tell you that in the name, place the Roman numeral. AU stands for gold. Now, what is the elemental symbol for gold? AU. When we find gold on the periodic table, boy, I should clean that up so we can use it again. Here's gold, AU. See how it's number 79? And it lies right in the heartland of, I don't know your charge by where you live, so I have to tell you the charge when I name it. AU is number 79. All right, so number 79 says there's 79 protons. It lost an electron to result in a +1 charge. We will name this as the gold Roman numeral 1, place it in a parenthesis there, gold 1 ion, the charge that it carries represented by the Roman numeral. Now here's AU 3+. So again, the identity comes from the protons. The protons will never change. There are 79 positive protons, but this time it lost 3. Loss of 3 electrons brings me down to -3, so that's 76 electrons. And now you hear this is called gold 3 ion. Gold 1 is a +1. Gold 3 is a +3. Letter C is the element SN. SN stands for tin. Tin is number 50 on the periodic table. That tells me that tin has 50 positive protons. Always tin will have 50 positive protons. If it results in a +2 charge, it lost 2 electrons, giving it a net +2. And if it lost 4 electrons, right, so here's loss of 2, loss of 4 negative charge. So the remaining must be +4. We name this as tin 2 in a parenthesis there. And this becomes tin Roman numeral 4 is an IV, tin 4 ion. So the positive protons identify the element. It's the electrons that are lost for metals or gained for nonmetals. Let's identify each ion. Oops, we have 27 protons in letter A. All right, 27. That looks like element cobalt, number 27. So I know that I have cobalt as my elemental symbol. Now, when I look to see, and this kind of got placed a little close together. Here's picture B, here's picture A. I need the proton number and the electron number for letter A. 27 protons told me the identity is cobalt. The net charge of 27 positives being balanced by 24 negatives results in a +3. So to name this, this becomes the cobalt Roman numeral 3, ion. Roman numerals required for these short elements called transition elements. Cobalt lives in the heartland of, I don't know your charge by where you live. You're a shorty. You're a transition metal. So I have to tell you the charge based on the Roman numeral. Here's another one. Letter B gives us 24 protons. So I've got to find number 24 on the periodic table. Oh, that looks like chromium right there, number 24. So identify the element as being chromium based on the proton number of 24. 24 positive protons being balanced by 22 negative electrons, resulting in a net +2 charge. So this would become the chromium Roman numeral 2 ion. I'm telling you the charge with the Roman numeral. Let's model sodium transferring its electron to the chlorine atom using Lewis dot structures and develop an electrically neutral compound. So this is kind of thinking about how many of each ion do we need to create an electrically balanced compound. So this, I'm going to start easy. Sodium lives in group 1A. It will form with its 1 valence electron. And while I'm here, I'm going to look for chlorine. Chlorine lives in group 7A, so it has 7 valence electrons. Sodium with its 1 valence electron, and chlorine with its 7 valence electrons. Did I skip a slide from here to here? I sure did. This is where we were starting. An ionic bond is going to form when a metal transfers its electrons to the non-metal. I sure did skip this slide. I'm glad I caught that. There's probably a fill-in here. An ionic bond is formed when a metal gives up its electrons and the non-metal takes them in. And the goal is to form a neutral compound where the overall charge is 0. Electrically neutral compound. So I wanted to model this picture, but I'm going to go through that step by step. Sodium, with its 1 valence electron, it lives in group 1A. So that's how I know it has 1 valence electron. As an atom, 1 dot. Chlorine lives in group 7A. That's how I know as an atom it has 7 valence electrons. Atoms are unstable. They would much rather have a noble gas configuration, and it does so by a transfer of electrons. The sodium electron will be given to the chlorine to form that partnership over there with that lonely electron. That's the 7th electron, unpartnered. And when it does so, we result with an ion of sodium, no dots, it gave it up, but it now has a plus charge. And you have chloride, who now has 8 dots and a -1 charge. Say the name of the positive just as it sounds from the elemental chart, sodium. Say the name of the negative, but change the chlorine to chloride, and we've written our first ionic compound. An ionic compound is composed of a metal ion, which we know is positive, plus a nonmetal negative ion, which we know is negative. Cation and anion, and the total charge must equal 0. So a positive one added to a negative one gives us a 0 charge overall. It's neutral. And that's what this is showing on that previous slide. If you're following, it says we have a sodium +1, we have a chloride -1, and it results in this ionic compound, this 3-dimensional crystalline solid in its repeating pattern. Here's sodium, here's chlorine, here's sodium, here's chlorine. Just this repeating pattern in 3 dimensions make a crystal solid. Formula units, commonly called salts, are always solids at room temperature, and they form these beautiful three-dimensional crystalline structures. When I call this a formula unit, it's the smallest representation of the repeating pattern in the crystal structure. The repeating pattern is 1 sodium to every 1 chlorine. That's what I'm referring to as the formula unit. The representative individual particle there of that ionic compound. And we determined the formula as NaCl, sodium chloride. Let's do this again for calcium and fluorine. So when we go to work and find calcium, its elemental symbol is Ca, and it's in group 2, so I know that it has 2 valence electrons. So calcium, who lives in group 2a, means it has 2 valence electrons. That's why it lives where it lives, as an atom, 2 dots. Fluorine is a halogen. Fluorine lives in group 7a, so I know that it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Now, as atoms, these are unstable. Atoms are unstable because they do not have the noble gas configuration. They want to form a chemical bond to create stability. The metal wants to lose, the nonmetal wants to gain. The trick here is seeing that when calcium transfers one of its electrons to the fluorine, that satisfies the octet of fluoride. He's done. He has 8 electrons. That's all he wants. And yet calcium has 1 more to give. So it's going to take another fluoride with its 7 electrons for the calcium to be able to give out its second valence electron. And when it does, it took 2 units of fluoride, each at a -1, to electrically balance the calcium, who now results in a +2. Calcium lost 2 electrons. It will be written as Ca +2. Each fluoride gained 1 electron. So I have 2 units of F-1. I'm just kind of showing the model here. This is an F-1. Here's the second F-1. Notice how 1 unit of a +2 with a -1, -1, 2 units of a -1 gave us 0 charge overall. Now let's write it as a formula. The metal will always be written first. The calcium, we had 1 of those. It took 2 fluorides, and that's where the subscript comes in. The subscript tells us how many ions were used. Calcium was a +2. It took 2 units of a -1 to create an electrically neutral compound. Say the name of the element for the metal just as it is, calcium. Say the name of the negative ion, but end it with IDE. We just drew an elemental ionic compound here known as calcium fluoride, CaF2. Let's challenge you to think that through a little bit. Let's suppose calcium, the magnitude of the charge is a +2. And think of that with fluoride, whose magnitude of the charge was a -1. Thinking about each positive having to be balanced by a negative, you can see why it took 2 fluorides to balance 1 calcium. So this is 1 Ca, and it took 2 units of the fluoride to create the same magnitude of the charge to be electrically neutral. 1 calcium for every 2 fluorides, +2, and 2 units of -1. Here's a little trick we're going to learn in a little bit. If calcium is a +2, I like to write its charge up high above the symbol. And fluoride I know is a -1. I like to write its charge up high over the symbol. And you'll hear me say crisscross. Crisscross the charges to find the subscripts. And this makes this whole task very simple. The magnitude of the charge is going to get crisscrossed. Bring the 2 around and down. The magnitude of the charge is going to get crisscrossed. Bring the 1 around and down. For every 1 calcium, it takes 2 fluorines. Now we don't typically write the subscript of 1. We leave it off and assume it to be 1 when we don't see a value. CAF2, the crisscross method. CAF2, little trick of puzzle pieces with magnitudes of charge. And using the Lewis dot structures, we determined how 1 unit of +2 requires 2 units of a -1 to create an electrically neutral compound. We just discussed ionic bonding for the formula of calcium fluoride. Let's challenge ourselves again for another model. Let's do between aluminum and sulfur. Okay, so challenge yourself first to figure out where does aluminum live and how many dots. Aluminum is right here. It's in group 3A. 1A, 2A, 3A. Group 3A. The tall columns are representatives. So that tells me aluminum will have 3 dots. The atom of aluminum has 3 valence electrons. Now we want to hook that to sulfur. All right, so let's find sulfur. Sulfur's right here. He's in group 6A. All right, group 6A means that he's going to need to gain 2. So group 6A tells me 6 valence electrons. Now these are the atoms. The atoms are unstable because they don't have an octet yet. They want to form a chemical bond to create an octet. Now, aluminum wants to lose 3 electrons. But how many spots does sulfur have to gain? It looks like it just has 2 spots. So this can only gain 2 electrons. So remember, this is the game. Let's start kind of fresh up here. Here's aluminum, 3 dots. Here's sulfur, has room for 2 more. Let's click and drag one at a time. Bring 1 electron. There's a loss of 1, plunk. Here's the next electron. I'll bring it over so that I can fill this. There's the loss over to sulfur. Now this guy's done. There's no more room there. And yet I still have another dot to get rid of. All right. So that tells me I've got to draw another sulfur. That way I can drag this 3rd electron and bring it there and drop it. That got rid of all of these, so it's a +3 charge. But we're not done yet because this sulfur still has an unpartnered dot. I'm not done. Everybody needs the right number of electrons, right? I gotta have everybody satisfying the octet. So draw another aluminum. One at a time, we're gonna drag this over. So here's the next aluminum, and I can fill this spot. Click and drag. That shuts down this sulfide. He's done. But this aluminum still has 2 dots left. They have to go somewhere. 1 more sulfur is drawn. So I can take the last 2 electrons and click and drag and bring them over. And when we did, we had all the electrons transferred. It took 2 units of aluminum to satisfy 3 units of sulfur. 2 aluminums, Al2, and 3 sulfurs, S3, Al2S3. This is a compound known as, say the first name, aluminum, say the last name, sulfide, ending in IDE. When we drew the Lewis dot structures, we had 1, 2, 3, 4, 5, 6 electrons transferred all together. In order to create a stable or an electrically neutral compound, it took 6 transferred electrons to achieve a noble gas. Let's remind ourselves of our trick we're learning called the crisscross method. You're going to love this. Remember how we said aluminum with its 3 valence electrons is going to form a +3 charge. We know that because we kind of predicted based on where it lives. Aluminum with its 3 valence electrons, when it loses those 3, it will result in a +3 charge. Sulfur, who lives in group 6, needs to gain 2. When it does so, it forms a -2 charge. And so when I think about what we're writing here, aluminum with a +3 and sulfur with a -2, write their elemental symbols with their charges up high, and here's the trick. Take the magnitude of the number, not the charge with it, but just the number, and crisscross to bring it down. Take the number, not the charge, but just the magnitude of the number, and crisscross to bring it down. Around and down helps us write the chemical formula Al2S3, aluminum sulfide. Think of it this way, another visual. Aluminum is a +3 charge. So I make that ion +3 big. Sulfide is a -2 charge. So I have 1 charge on aluminum not yet satisfied. So I draw in another sulfide, but he only comes in groups of -2. So I draw in a next aluminum. Plus, plus, plus. Aluminum only comes, that's not very good. Aluminum only comes in +3 units. I would like to make them about the same size for effect. That tells me that I have sulfur with a minus. That sulfur comes in only -2 charges. It takes 2 aluminums at a +3 apiece and 3 sulfurs at -2s each to create an electrically balanced compound. 1, 2, 3, 4, 5, 6 positives, 1, 2, 3, 4, 5, 6 negatives, and we're balanced to be electrically neutral. We have 2 units of aluminum, electrically balanced by 3 units of sulfide. Aluminum sulfide is our compound. So we've really done some good practicing, kind of setting up what we call the crisscross method when we write out our formulas. And I'd like to come back in our next video and just practice writing binary ionic compounds from the name, and then naming binary ionic compounds. So take a break, come on back when ready.